The clearest signs yet that Mars may have once hosted life. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. NASA's Perseverance rover has uncovered intriguing chemical clues inside a sample called Sapphire Canyon, collected from the rock nicknamed Cheyava Falls in Jezero Crater's Bright Angel Formation. The chemistry points to potential biosignatures, hints that ancient microbial life may have once existed on Mars. We'll begin with a clip from Morgan Cable, research scientist at NASA's Jet Propulsion Laboratory and co-deputy principal investigator of the PIXL instrument on Perseverance, as she explains the importance of the sample. Then explore the details with Joel Hurowitz, lead author of the new Nature paper analyzing the results. And later, Bruce Betts, our chief scientist, joins me for What's Up, where we'll look back at earlier moments in the exploration of Mars where scientists and the public alike were thrilled by hints of life. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. NASA's Perseverance rover has been exploring Jezero Crater since 2021, a place once home to an ancient river delta where water flowed into a vast Martian lake. The rover's continuing mission to search for signs of past habitability and to collect rock cores that could someday be returned to Earth for analysis. Then, in July of 2024, Perseverance drilled into a rock in the Bright Angel Formation. That's an ancient riverbed on Jezero's western edge. The team nicknamed that rock Cheyava Falls and then sealed the resulting sample into a titanium tube. They nicknamed the sample Sapphire Canyon. Over the past year, scientists have been poring over the rover's data, finding intriguing signs of organics and unusual mineral patterns nicknamed poppy seeds and leopard spots. Together, they may represent the strongest evidence yet of chemistry that on Earth is often tied to life. But these aren't fossils, and they're not definitive evidence of life on Mars. Scientists are calling them potential biosignatures, features that might be explained by biology, but also could have formed through non-biological chemistry that we have yet to understand. On September 10th, NASA announced these findings at a press briefing and through supporting videos and articles online. In one of those, Dr. Morgan Cable, a research scientist at NASA's Jet Propulsion Laboratory and co-deputy principal investigator of the PIXL instrument on Perseverance, explained why the Sapphire Canyon sample is so important.
Our first reaction on the team when we saw this rock was like, whoa, what is that? What could have caused that? Sample 25 is called Sapphire Canyon. This is a core that was collected from the Cheyava Falls rock in Neretva Vallis. The Cheyava Falls rock is really neat. If you look at it, it's got all sorts of cool features. It has these small black spots that we call poppy seeds, and also these larger spots that we call leopard spots. This is the only place we've found on Mars so far where we have chemical evidence that chemical reactions associated with life could have been happening, as well as organic molecules. The Sherlock instrument detected an organic signature. So both of those together in the same rock is really compelling because these similar types of features, when we find them on Earth, oftentimes they're associated with biology, with microbes. And so those pieces of evidence combined together, we believe justify calling it a potential biosignature. I would describe the Sapphire Canyon sample as mysterious because we see these signatures that tell us chemistry has happened, potentially involving organics, but what does that mean? Could life have been involved or something that didn't involve life at all? We're not going to know until we bring that sample back and do some more measurements.
At the September 10th press conference, scientists dug into the details of the discovery, including Dr. Joel Hurowitz, who led the Nature paper analyzing the sample. The study highlights one of Perseverance's most intriguing discoveries so far, these unusual patterns in the Bright Angel rocks, tiny nodules they nicknamed poppy seeds and leopard spots. Perseverance's instruments revealed that they contain iron phosphates and iron sulfides, closely associated with organic carbon. On Earth, those minerals are often formed through microbial activity, which is why the team is calling these potential biosignatures. I spoke with Joel about what Perseverance found in the Cheava Falls rock and why this particular rock sample, Sapphire Canyon, is raising so much excitement. Joel Hurowitz is an associate professor of geosciences at Stony Brook University. He earned his PhD in geosciences there in 2006, after his early work as a hydrologist. He went on to be a postdoc at Caltech and a research scientist at NASA's Jet Propulsion Laboratory before he decided to return to Stony Brook as faculty in 2014. Joel is also the deputy principal investigator for the PIXL instrument on NASA's Perseverance rover, and much of his research connects Mars exploration with analog studies here on Earth. His group investigates how iron-rich and basaltic environments record signs of water, habitability, and potentially even life. Their new paper, called Redox-Driven Mineral and Organic Associations in Jezero Crater, Mars, was published in Nature on September 10th, 2025. That's the same day as the press conference. It's a collaboration between many co-authors on the Perseverance science team, including our own Planetary Society board member, Dr. Jim Bell. Here's my conversation with Joel Hurowitz. Hi, Joel.
Hey, how are you?
Doing really well, and even better now that we have this wonderful new paper on this sample from Mars. I tell you, me and my coworkers have been hoping to get more information about this ever since we first learned about it. So I'm so excited to hear about this announcement.
It's a really super exciting thing to be a part of, for sure.
And now you're at the crux of this news story that I think people who are super passionate about science are excited about, but it's also tapped into something in the general public. Like anything that has to do with the search for life, and any headline as big as this is a potential biosignature on another world, that's got to come with a whole flood of commentary from people and interactions you might not have expected.
Yeah, it's been, I guess maybe I shouldn't be as surprised as I have been, but the level of interest has been amazing. Like, I would say, like, in the couple of days leading up to the release of the paper in Nature and the Associated Press briefing, the interview requests started to come in, and it has not stopped since then. So this is, now like 2.5 weeks, and it's been, by and large, quite positive. People are really sort of curious and excited about the possibilities here. I've gotten some kind of fun emails, I guess, from interesting characters in the world who have strong opinions about these things. But that kind of, I guess, just goes with the territory. But it's been really exciting, I guess I would say.
Well, I learned about this last year. It was July, and I was at Caltech for the 10th International Conference on Mars. And on the last day, someone went up and presented these images of the Cheava Falls area, the rock, and the samples that were coming out of it. So I just happened to be there when it was first announced, and people were very excited about it. But what has happened in the last year and more recently that's brought this story back into the press?
Yeah, so I remember that same time period. It was, summer of 2024, and I Mars, that conference was in July. Is that right?
Yep.
Last year? Yeah. So we were sort of getting our first observations of the Bright Angel Formation that the Cheava Falls rock is a part of, in the sort of month leading up to that. And I mean, we kind of knew right away that there was something like really interesting and exciting going on in these rocks. And, I think that the reason to hold that briefing at that time was like the images of these rocks, they go out to the public really quickly. And it seemed like it was a good time to sort of give folks a heads up that, like, hey, we're into something really interesting here. We're still trying to figure out what it all means, but it looks exciting to a geologist and a geochemist, right? And then in the interim time since then, we spent, I want to say, another month or two roving around inside of the Neret Vivalis channel, investigating more of the rock outcrops that the Cheava Falls rock was a part of, really trying to like firm up our understanding of the environment that those rocks were deposited in. And around maybe September of 2024 was when we really started putting, I'll say, pencil to paper, but really I'm, typing away, putting, the manuscript together, interpreting the data that we were collecting. And that went on for probably 2 months or so. It's probably the fastest I've ever turned a paper out into something that, could be, that was ready for submission. Submitted the paper in November after a bunch of sort of team internal discussions and reviews and making sure that everybody was on board with the interpretations. And then the rest of that time between November and September, I guess, sort of June or July or so was the review process. So we went through 2 rounds of review with our peer reviewers. And then the rest of that time was kind of just getting everything lined up and scheduled at the journal for publication. So we were just sort of working and responding to reviews during that entire time period.
But it's really exciting to finally have a published paper in Nature to make sure the whole thing is peer reviewed. Like it's a huge claim to say potential biosignatures in a rock on Mars. But now that it's had so much more review, now we can confidently say not that this is actually evidence of life on Mars, but that we found something really interesting here that really makes a case for bringing these samples back.
Yeah, no, that's absolutely right. The observations that we made with the full instrument suite on board the rover, it's everything that this payload was designed to be able to do, right? The observations that we've collected are, they extend from the sort of outcrop scale images to the subsurface ground penetrating radar data that really lets us sort of build a picture of the environment at the time that the rocks were being formed, all the way down to the micro scale of these little nodules and reaction fronts and their interesting mineral enrichments and organic matter that could plausibly be explained by the activity of microorganisms that do similar things on Earth, but that, might also have other non-biological explanations. But I think that's about as far as anybody can be expected to go with a rover 200 million miles away from the Earth that is operating and investigating rocks that are somewhere between 3 and 4 billion years old. I
mean, I think so many people are just so hungry for the announcement that we found life off of Earth. But if we take a step back here and just think about how much we've accomplished and the fact that we're even able to say that we've drilled these samples on Mars and that we're finding this possible evidence of past life there, it's far beyond where I expected we would be when I was a kid. And it's a really exciting time and potentially signals that we're right on the edge of some of the biggest discoveries in the history of history.
Yeah. No, I mean, I think you're right. And the key next step is to bring this sample that we collected back to Earth. I mean, this paper and the analyses we did, there are a large number of open questions, right? And I think there's some amount of work that people are going to be able to do here on Earth without the sample, right? In laboratories, they can go out into the field, they can look for analogous settings on Earth where similar suites of minerals and chemical reactions are taking place to what we observed in the Bright Angel Formation. But my suspicion is that we'll get to a place where there's a community of people who have said, I've figured out a way to do this without biology. And a community of people have said, well, yeah, but I've also found ways to do it with biology. And hopefully, in sort of performing those investigations, we'll develop the tests that we would want to run on this sample to determine which of those two is the right option. But that means the sample's got to come back.
And we have to figure out protocols for containment and how to do all that just in case. It's a compounding problem that I'm sure gets more and more complex as we think about it, but an absolutely worthy science to do. But Perseverance landed back in Jezero Crater in 2021, which feels like it was yesterday, but also a million years ago now. And since then, it's been exploring around that river delta and then making its way up to the rim of the crater. Where is this Bright Angel Formation in the context of those travels?
So the Bright Angel Formation is like right on the sort of like off ramp out of the crater. It's so we landed on the crater floor and investigated the rocks there, and they turned out to be a suite of igneous rocks. There are a bunch of lava flows, and then potentially some rocks that represent like magmatic intrusions into the crater floor itself. And then we drove off of that crater floor unit up into the delta. So we investigated the front of the delta and then the top of the delta, and confirmed that indeed it was a delta, sort of formed in the way that we expect it to have formed, via similar processes that we observe on Earth. It's a river flowing into a lake and depositing sediments into that lake. And then we went into this unit called the margin unit, which is kind of this strip of rock that sits between the delta and the rim of the crater. The margin unit has been kind of a puzzle for us, and still is, despite all our capabilities. We have a variety of opinions on the team about exactly what that unit is and how it was formed. But it's geochemically and mineralogically really exciting. It looks like, it's a bunch of igneous minerals that have been converted into carbonate minerals and silica. So there's a whole history of like water rock interaction recorded in those materials, and whatever they turn out to be, we will figure it out when we get those samples back to Earth. But just before we drove off of the margin unit and out onto the crater rim, we had been planning to drive down into this river channel that cuts through the margin unit and was basically the feeder system for the sediments that formed the delta. So we drove down into that river channel, and in the walls of that river channel, that's where the Bright Angel Formation is located. And that's where all of these findings come from. It wasn't happenstance that we ended up in that river channel, but boy, did we ever have some good fortune that we planned for the long term to always want to go check those out, because they turned out to be super exciting rocks.
Well, what makes the mudstone and the conglomerates in this Bright Angel Formation kind of stand out compared to the other layers in Jezero Crater?
There's a bunch of things. So looking down at the planet from orbit, they kind of stand out as being kind of like light toned, kind of layered looking rocks that you can see kind of exposed in the walls of the river channel. But when you see them up close, they are the finest grained sediment that we've really seen on the mission. There are some similar-ish rocks down in the delta front, but they have a very different chemical character to them, and they may or may not be quite as fine-grained as these rocks. For me personally, and I'm not a sedimentologist, so maybe a sedimentologist wouldn't be surprised by this, but I wasn't expecting to find like the finest grained mudstones that we'd see in a river channel. Usually you think of a river channel, you think water's moving by really quickly, you're going to have lots of coarse sediment in there, and the mud will bypass that part and get deposited way out in the lake. But somehow the mud's settled inside of this river channel by a process that may have included the river channel actually getting dammed up at one point and kind of backing up behind that dam, perhaps by a landslide or something like that. Mm-hmm. There's a paper that's actually submitted to a journal that suggests that that's the right way to interpret why this river channel got filled up with mud. And then not only are they like super fine grained, but chemically they're incredibly distinctive from any other sediments that we saw in lower down in the delta. They're really oxidized, meaning they're really rusty, and they've been sort of chemically leached of a number of elements like their magnesium, their calcium has all been sort of removed from the rock. That's the kind of thing that happens when you have rock exposed somewhere outside of the crater that's being chemically weathered. It's being leached maybe by rainfall pumping through it. And then that material, that weathered material, then gets kind of flushed down into the river system and deposited as these muds. We didn't see anything like that earlier down in the delta that was either that leached or quite that oxidized. And so I realize there's a long story here, but I think what's cool about that is that it tells us that at some point in the history of this river lake system, the environment was not really doing much chemical leaching. It wasn't very oxidizing. And then the sort of climate and atmosphere changed in a way that provided a new type of sediment where the material was being oxidized. It was being chemically leached. So I think it's giving us a sense that the sort of climate of the environment around Jezero Crater was dynamic and sort of, changing rapidly in time.
Which gives us a good way of kind of learning more about the history of that area, right?
Yeah.
And Perseverance's Sherlock instrument picked up evidence of complex organic carbon in this mudstone as well. And it did it by specifically looking at this kind of G-band signal, it's spectroscopic peak. That's kind of a a fingerprint of kind of more aromatic carbons or, graphitic stuff. Can you explain what that signal revealed to us about the types of organics that are kind of present in these Martian rocks?
What this means is that we can identify that these rocks have a sort of complex, what we call macromolecular organic carbon in it. That type of carbon can have a variety of sources. And I sort of feel like the Nature paper is sort of the first wave of information that's going to come out about these rocks. And so I'll say that there is another paper that is going to follow the Nature paper up that describes in much more detail exactly what we can say about that organic matter. But it's the kind of sort of high molecular weight carbon compound that can form by a variety of processes. You can find it in meteorites. You can find it in, being synthesized in hydrothermal systems as a result of, high temperature water rock reactions. You can also find it as the sort of like the degradation product of biologically sourced carbon. So there's a bunch of ways that you can get carbon like that into these rocks. And again, this is one of these questions where to really determine what the origin of the carbon in these rocks is, we're going to need laboratory analyses back here on Earth.
Yeah. And there's also this whole other thing going on where we found these organics in places like, Cheyava Falls or Apollo Temple, but not in other places like, Masonic Temple, I think is the example I'm thinking of. I'm trying to figure out why that's the case, because it's not surprising necessarily that there are complex organics, but it's surprising to me that there's such a different kind of population of them depending on where you are within Jezero Crater.
Yeah, I guess a couple things kind of stand out to me sort of in reflecting on that question. It is like, one, why is it that the most oxidized sedimentary rocks that we've come across are the ones that have organic matter in them? That's kind of interesting and maybe not what you would have expected, just, kind of knowing that oxygen and oxidants and organic matter don't really like each other very much. But there was something about the environment at that time that favored the accumulation of organic matter in that part of the lake when Bright Angel was forming. Maybe it's just because these are muds, and muds are really good at preserving whatever organic matter is sort of, raining out of the water column along with the mud and protecting it. That would make some sense. But the other thing, to your question is like, why is it present in some types of rocks in the Bright Angel Formation and not in others? My sort of gut sense on this one is that when the mudstones were being accumulated in the sort of north side of the Neretva-Vallis Channel, that those muds were sort of slowly accumulating as mud settled out of the water column to the lake bed. And under those conditions, whatever organic matter was in the water column was also settling down onto the lake bed with those muds. In the other places where we didn't see the organic matter, like over in Masonic Temple, those are conglomerates. And so they're deposited really quickly, probably because of like debris flows or things like that, maybe coming in off of the crater walls. And so maybe there just wasn't time for the organic matter to accumulate in the same way, because those sediments kind of they just came in as a pulse rather than through gradual accumulation. So that's kind of my guess as to why those differences are there.
Well, as we're looking at this rock, there are two kind of very distinctive features, the poppy seeds, as they're called, and these leopard spots. Mm-hmm. So let's start with the poppy seeds. What are these things in the rock? Yeah, so they are sort of 100 to 200 micron diameter mineral accumulations, where the mineral that is in these little poppy seeds contains both iron and phosphorus. And based on the chemical properties, their color properties, and some of the elements that they don't contain, like aluminum, we think that they represent little nodules of a mineral called vivianite, which is Fe3PO4 2 and some water molecules. And probably
there's a good chance they're not, pure vivianite anymore, because vivianite on Earth, if you expose it to air or any oxidants, it starts to kind of change its mineralogy to something a little more oxidized. So our guess is that it started out life as vivianite, and then as it's been exposed to the environment on Mars, it's probably changed its character to something a little bit more oxidized than the original vivianite that was there.
Mm-hmm. So the host rock is mostly made out of this like oxidized rusty iron. And then you have these poppy seed nodules that are made out of this iron mineral called vivianite.
Yeah. Why
is finding this kind of like reduced iron phosphate inside of an oxidized rock important?
Yeah. So it is providing evidence that a redox reaction took place, that there's an electron transfer process that took the iron in the mud, this ferric iron, iron 3+, and turned it into iron 2+ via reduction. And the partner, the thing that actually donated those electrons, is we think it's the organic matter in that rock, right? So there's a ferric iron in the mud and organic matter in the mud. And as those two things sort of settled out on the lake bed, the organic matter and the ferric iron reacted with one another to produce iron 2+. It reduced the iron in the mud to this other form of iron that could then combine with phosphorus to precipitate vivianite. And that reaction between ferric iron in the mud and organic matter in the mud, this is one of these things that has a potentially biological origin, because when we see those two ingredients being deposited in, muds around the world today, in marine settings and lake settings and estuaries, there's a population of microbes that are basically eating that organic matter and facilitating that redox reaction that ends up making vivianite as a byproduct.
Mm-hmm. Those are the poppy seeds. And then we have these leopard spots, which I just think are just so cool and so weird. What makes these leopard spots so visually and chemically distinct from, say, like the poppy seeds?
Yeah, so they're bigger. They're more like a millimeter or two in diameter. They have a dark rim and a bleached sort of white toned interior. So they kind of stand out. Like you see them, you're like, what are those things? And you've got the sort of reddish colored mud, and the rim on the leopard spots is more of that vivianite material. So it's the iron phosphate that makes up the rim. And then inside of the leopard spot, the reason we think that has this sort of bleached color to it is it's because the rusty red iron has been removed from the core of the leopard spot and exported into the new mineral phases, the vivianite. And then in the middle of the leopard spots, there's another new mineral, this greigite, that is an iron and sulfur bearing mineral. It's an iron sulfide mineral. So there's kind of there's almost like a stratigraphy, from the inside to the outside of the leopard spot, where you have a couple of different types of minerals in there, and colored properties changes.
How do we know that these spots kind of represent reaction fronts that formed in place rather than something that was kind of deposited around it?
We thought this through some, and what we concluded was that if you had 100 or 200 micron diameter vivianite grains, or millimeter scale, I don't know even how they would come to be, but I guess sort of grains that were rimmed in iron phosphate and at their core had iron sulfide in them, they would have a different density than the surrounding sediment that they're deposited in. So as this material is being kind of like flushed into the system, they would have separated themselves out from the mud around them into like laminations that would be enriched in poppy seeds or enriched in leopard spots. And then you would have layers of mud, and those things might alternate. And that would be a real clue that like, oh, these were actually sort of delivered by moving currents, and they settled out onto the lake bottom this way. They just appear to be sort of randomly dispersed throughout the sediment. It doesn't look like they were deposited and separated by sort of, density differences. And honestly, I like the reaction fronts, the leopard spots. There's no way those things are grains. They just look like they formed right there. I would have a hard time making those into grains just based on their visual appearance.
Mm-hmm. So how is your team interpreting the sequence of redox reactions that transformed all this ferric iron into these reduced minerals?
Yeah. So the way we imagine this happening is that you had little bits of organic matter in the mud, and by whatever process the organic matter in the mud were reacting with one another at the expense of that organic matter. So you would consume the organic matter and make new mineral as a result of its reaction with the mud. And in the places where the poppy seeds form, maybe you just ran out of organic matter in that little local environment. There just wasn't enough for it to sort of continue reacting. Whereas for the leopard spots, perhaps there was I almost want to call it like a bigger chunk of organic matter. So as you were kind of reacting that organic matter with the surrounding mud, the vivianite producing front continued to migrate sort of outward away from that organic matter. And at some point you run out of ferric iron to react with.
Mm-hmm.
And so the next thing that might be available to react with would be sulfate that's maybe dissolved in the sort of mud water slurry at the bottom of the lake. And so the organic matter then might start reacting with the sulfate to make reduced sulfur that can then combine with ferrous iron to make greigite, to make the iron sulfide mineral. So it's kind of almost like a ladder of redox reactions taking place.
Yeah, that's interesting too, because the paper describes this kind of inverse relationship between the abundance of reduced minerals and how red the surrounding rock is. Why is that so important?
Yeah, so I think what it tells us is that these sort of bleaching reactions that were taking this initially rusty red, mud and turning it into new mineral phases, it went as far as it could based on how much organic matter was there to begin with. So in cases like, Apollo Temple, which is the abrasion patch right next to Cheyava Falls, there was enough organic matter there that these redox reactions were actually able to almost kind of completely bleach the rock of its ferric iron. And in other places, like at one of the other targets, like Walhalla Glades is the name of another target, the bleaching wasn't quite as extensive. So the rock still has a kind of tan color to it. And maybe what that means is there just wasn't as much organic matter available there to complete that bleaching process. And that bleaching process is a direct result of these redox reactions that make these new mineral phases.
We'll be right back with the rest of my interview with Joel Hurowitz after this short break.
Hi, I'm Danielle Gunn, Chief Communications Officer at the Planetary Society. We're proud to support International Observe the Moon Night, NASA's annual celebration of our nearest neighbor in space. This event brings together skywatchers, families, students, and communities worldwide to share in the wonder of the moon. Whether you attend a local gathering, host one yourself, or simply step outside to look up, you'll be part of a global movement to connect with our moon. International Observe the Moon Night takes place on and around Saturday, October 4th. Explore activities, download custom moon maps, and find events near you at moon.nasa.gov/observe. However you choose to participate, outdoors, online, or from home, you're invited to celebrate the moon with the world.
So we've been talking about a lot of rock reactions, what this has to do with organic chemistry. But the real headline here is that all these might be potential biomarkers. And from a geochemical standpoint, how plausible is it that this vivianite and greigite could have formed at these low temperatures without any kind of biological process?
Right. So I break it out in terms of the two mineral phases. So I think it's easier to make the vivianite in the absence of biology. I have not seen the laboratory experiment where somebody went in and took macromolecular organic carbon and ferric iron rich mud and incubated them together and turned it into vivianite. We went through the literature. We tried to find examples that might say this can be done, completely in the absence of biology. We didn't find that experiment. It doesn't mean that someone won't in a week, go off and do that experiment and publish that finding. And it's well known that ferric iron and organic matter are quite reactive towards one another. And so the redox reactions that make vivianite, it feels plausible to me that someone will figure out that can be done, completely abiotically. The production of the iron sulfide mineral, the greigite, that's a tougher ask. And the reason is that the reaction between sulfate and organic matter at like room temperature conditions, it's incredibly slow. So slow that we don't actually observe it happening in natural environments on the Earth. Where we do see it happening is where either one, biology is involved, but sulfate reduction is a metabolism that microbes will make use of to generate energy. The other place that this can happen is if you take sulfate and organic matter and you cook them together at temperatures above about 120 to 140 degrees centigrade, then you can kind of overcome that kinetic inhibition that exists at lower temperature, and you can drive the production of reduced sulfur bearing minerals. Now, I guess sort of two things on that. One is, again, I don't know if the experiment is out there where somebody tried to replicate the initial state of the bright angel system and then heated it up to make these minerals. But someone needs to go out and do that experiment. I think it's really important. The other aspect of this, of course, is that, we spent a lot of time in Neret Vivalis and in our paper trying to figure out whether we could find any evidence that the rocks had been heated. And within the limits of our payload's capability, it's just not obvious to us that it has been. So to us, the sulfate reduction reaction seemed more plausibly low temperature. So I think that's probably the one that is has a less obvious non-biological origin. Again, unless it turns out that we just can't tell when rocks have been heated to 120 degrees with a rover payload, in which case that will have been the answer. We weren't able to detect that subtle temperature difference.
I mean, all the more reason why we need to get these rocks to Earth so we can test them, right? But I do love that this paper, you and your co-authors really do stress that even though there could be biological reasons for this, there could be biological reasons for this. Yeah. And, there are alternatives to this being life on another world. But I mean, that's absolutely wild. Just on the face of it, it's hard to explain.
Yeah.
So I get why people are so excited, but we do have to be very mindful when we're making claims like we found life on another world. I know people want to jump to that, and we all as scientists want to get to that answer, but we have to take this step by step. And NASA and the astrobiology community, they often refer to this confidence of life detection scale. Yep. And that's part of how we assess these discoveries. Can you talk a little bit about that scale and where would you place this Sapphire Canyon sample on that scale today?
Yeah, this has been another one of these sort of like educational things for me, is learning about the cold scale, the confidence of life detection scale, as I've sort of grown into a role as like, I'm not an astrobiologist, but I play one on TV kind of. So I've actually found that scale, maybe not surprisingly. I mean, it's a really nice piece of work, and it has helped me to sort of figure out where this detection sits on that scale. Anyway, that's all kind of, preamble to like, where do I think it sits? So I think that it sits at step 3 on the cold scale, which is like, interesting. I guess step 1 is like interesting, potentially biological signal. Step 2 is that you have ruled out contamination as a source of that signal. like, these are rocks. We have determined that the organic matter in those rocks is not just like a surface phenomenon that's shed off the rover. It's present in the abraded patches. It's present, and its sort of distribution in the rocks makes sense from a paleoenvironmental perspective too. So I mean, I don't know how the poppy seeds and leopard spots would be contamination, and I don't think the organic matter is either. So that takes us past step 2. And then, step 3 is this signal, at least in my interpretation, is this signal coming from an environment that we know is a plausible host for biological processes, right? So it's sort of building that geological context. And that gets us onto step 3. And I think we've established that this is a plausibly habitable environment that could have had biology in it and preserved signatures of that biology. I think step 4, it's a really big step. It's like, now you've ruled out all known sources of non-biological signal. I guess you've ruled out all non-biological processes to make that signal. I think I sort of feel like we're on step 3, and we started lifting our foot off of step 3 and are trying to put it down on step 4, but we're not there yet. And I think getting up to step 4 is going to be the work that follows this paper, the work that people do in labs, the work that people do on Earth here, and then ultimately, the work people will do on the sample if we ever get it back.
We'll call it step 3.5.
There you go.
But really, there's so much work that needs to be done in order to figure this out, right? We need to figure out if there are biological processes for creating these rocks. But more profoundly, I think we just need to get those rocks down here to Earth so we can do some testing on them. Yeah. What kind of analysis on these rocks would you personally be most interested to see happen?
So I guess there'd be a couple of things that I would be most excited about. One class of analyses would be isotopic analyses. So I would love to see paired analysis of the iron isotopic composition of the mud and the iron in the greigite and the vivianite, because those things are related to one another by a redox reaction. And the magnitude of the difference between them and the sort of the sign of the difference in their isotopic compositions could be very telling in terms of whether or not biology was involved. This is a tool that we use in trying to understand whether the oldest rocks on Earth have been formed as a result of biological processes. We always go to isotopes. And the fact that we have the mineral pairs all in the same rock, that's actually that's exactly what you want. So we've got that set of isotopic measurements. We can do the same on the sulfur between the greigite and the surrounding sulfate-bearing mudstone. And then there's there's carbon in multiple redox states. There's the organic carbon, and then there's a little bit of carbonate in the rock. So we can throw like 3 isotope systems at the problem to try to see whether they're telling a sort of internally self-consistent story about differences in isotopic composition that are offset, in ways that we know biology does on Earth. And then, of course, there's like all the things that I guess like an organic geochemist would do, like what is the organic matter? Are there little, like lipids preserved in the rock? Like, I can imagine all kinds of like microscopy and things that would, be done on these rocks to try to figure out, what other potential biosignatures might be contained in them. But that's kind of not my area of expertise, so I tend to stray away from it.
Really, though, I just really hope that this Mars sample return mission happens and that we get these samples back here. Because even if it's not just this sample, the entire history of everything we've picked up on Mars with this rover just tells such a compelling story about how this world has evolved and what it might have been like in the past, whether or not it might have been habitable. It just kills me that they're just sitting there on Mars waiting for us.
And well, we're still collecting. We're not done yet.
Yeah.
We've still got 6 tubes left to fill. So, and there's more, exciting things left to collect before we finish that job.
Right. But in the meantime, it's like, this is it's a weird thing to say, but it is one of the most compelling bits of evidence of potential biosignatures on another world that we've detected so far. And there's some really wacky things going on out there in some of those ocean moons.
Yeah.
But this is just so compelling and so exciting. But how do you balance the public's understandable excitement about a story like this with phrases like, "This is the closest we've ever come to life on Mars," with the true story of this, which is that it's really complicated and we're still trying to figure it out?
Yeah, you tell me. Am I doing it? Have I done a good job of balancing it?
Yeah,
It's
complicated.
It really is, and you want to. I think all we can do as scientists is sort of convey how excited we are about this and the potential of this discovery, while also sort of conveying that there is uncertainty here, and that there are steps that need to be taken to reduce that uncertainty. So, I think we have to be really careful not to say anything like, this is a slam dunk, we've discovered life on Mars. Like, that's not what we're saying, but we're saying we've discovered something really exciting that with additional work might tell us whether or not Mars was ever inhabited. And maybe that kind of speaks to sort of a bigger picture question, which is like, wouldn't you love to know the answer of whether or not there was ever life on a planet other than the Earth, right? So like in that little tube, the answer might be there, So it's a tricky balancing act, but hopefully if nothing else, folks sort of get the sense that of our excitement, and maybe that sort of rubs off in a way where they're like, well, wow, there's something really cool going on here that we want to know more about.
Well, I tell you, it's so compelling that anytime we're doing our space advocacy work in Washington, D.C., I'm walking around with Bill Nye. He has a 3D printed sample container from Perseverance that he keeps in his pocket at any given moment, because it's things like that. It's physically holding it in your hands and imagining a world where that's in our science labs and we're testing those rock cores. I feel like that's one of the most compelling things I've ever seen when we're talking about why we love this kind of science so much and why it deserves so much love and attention. So I just want to say a thank you to you and everybody else who's done such thoughtful work on this, because you're not jumping to conclusions, but you're also giving us hope that we'll be able to answer one of the greatest questions humanity has ever posed, maybe in our lifetimes. And that is super exciting.
Yeah, well, I mean, yeah, and it's incredible to be able to be, a small part of that. I've been doing this type of work since I was, 20 something years old as a grad student, and I've been incredibly fortunate to have, had mentors that have enabled me to participate in Follow the Water, right, on MER. And then it was like, all right, well, we found the water. What's next? Was that water habitable? Let's go explore habitability with the Curiosity rover. Yes, Mars was both water rich and habitable. And now to be in that sort of final stage of that exploration where we're actually seeking the signs of life on Mars and finding things that could be signs of life on Mars. It's been such a cool, like, natural progression in our exploration where we're sort of, doing step by step kind of incremental, increases in our knowledge. And, as you said, we have one more step to go here. And that's, a future mission to get these awesome little tubes, back into our labs on Earth.
Well, fingers crossed we make it happen. And then a whole new generation of people is going to get that much closer to this intersection between geology and astrobiology. And it's going to be one of the most inspiring things that's ever happened in the history of science. I keep saying it, but really, this is a moment. And I hope people get a chance to read this paper and learn more about it. And I'm looking forward to all the other papers you mentioned during this, because this is just the beginning of some much more complex science. This is an ongoing process. And I wish you and all of your colleagues, like, the joy of discovery. I think this is a fun process, even though it is complex and often, very nitty gritty and sometimes frustrating. But you come out the other end in a moment like this, and it is worth every single moment.
Yeah, absolutely. Yeah. Thanks so much.
Well, thank you. And seriously, good luck.
Thank you. I appreciate it.
Perseverance's discoveries are the latest chapter in the long history of tantalizing clues from Mars. This week on What's Up, I asked Dr. Bruce Betts, our chief scientist here at the Planetary Society, to look back at some of those earlier moments when scientists and the public were thrilled by the possibility that Mars once hosted life. Hey, Bruce.
Hello, Sarah.
I'm glad that we get to finally dig a little deeper into these Cheava Falls samples. Like, we learned a little bit about them last year when we first got this result, but now we have some serious peer-reviewed science on it. And while it doesn't show clearly there was life on Mars, like, this is still really exciting.
It is, and it doesn't. So yes, correct.
It's true.
Generally, the answer is not life, just like on Earth, it's not aliens. But this is one of the most interesting things, as I'm sure you discussed, that we've seen in the possibility of getting it back someday and throwing it into some nice, big, gnarly instruments and really finding something out is exciting. I mean, they've done an amazing job with what they had. They used everything and the kitchen sink, I think.
The kitchen sink instrument on Perseverance.
Yes. Little known kitchen sink instrument.
Now, it really does cement the fact that we need to get these samples back from Mars. We need to get these samples back from Mars. There are good reasons why people are so excited about this result. And there have been a lot of results throughout the years that have kind of pointed to this possibility of life on Mars, either in the past or even in some cases, extant life that exists today. All of that is still hotly debated. But while we're in this moment talking about Martian exploration, can you talk us through a few of those big moments and what we've learned from them on Mars?
Sure, that's not a big topic. I can handle it in the next 30 seconds or so.
Go!
Let's start way back, going all the way back to, I believe, William Herschel in the 18th century saw the polar caps that Mars has getting bigger and smaller with seasons. And then you took that, and then people, as they got better telescopes in the 1800s, they started seeing dark areas and bright areas and variability, and they started talking, what if those are oceans and land? And if you've got oceans and land, then you got life. And then you had Schiaparelli and then of course Percival Lowell, who came along and ran with what turns out to be an optical illusion of our brains, which is connecting things with straight lines. And they reported canals on Mars. So now they were moving water from the polar regions. Anyway, led to War of the Worlds, the fictional book, not an actual war, and churned up a whole lot of great science fiction and crazy ideas of Mars. And then we went there with Mariner 4, 6, and 7, the first flybys. And Mars has different terrain, and with their resolution, they've all happened to fly by the really lunar-looking part of Mars. So then it's like, oh, Mars is dead. Never mind. And then Mariner 9 came along in 1971, and it's like, holy crud, look at those channels and those things cut by liquid water, life. Ooh, yay. And then they sent the Viking orbiters, and they got much better data, and the Viking landers. And the Viking landers had 3 experiments designed to test for life, but they were very specific. 2 of them were like, no. One of them, last I knew, was still being debated, but by and large, the community thinks is not an indication of life. It was where they poured some happy little nutrients in, and then they got out gas that you could call life. But it turns out Mars has a bunch of other stuff in the well, it's not technically a soil, but the dirt, including perchlorates that do funky things in the chemistry. And then there's just been all sorts of things studying habitability, including with the rovers as well as from orbit, seeing things associated with liquid water, which is one of the 3 things that all life needs on Earth. And it's not really there much right now, except maybe underneath the ground, but that's tough to get to. But a lot of evidence of past, a lot of evidence of happy, friendly liquid water in some of the rover locations. And now you've got, leaping ahead, the things that you talked about on the show. But there's also things like detecting methane in the atmosphere. And the thing with methane is It is calculated to have a lifetime of a few hundred years before it gets destroyed by the ultraviolet, but by something, maybe little methane creatures that eat it. No, that's not it. But the methane could be produced geologically, volcanic action, which is interesting, or it could be produced by life, or it could have issues with measuring such a tiny amount of methane. But they've focused more on that and seeking out trace gases with the orbiters. And so there's still this kind of, maybe there's some kind of life going on. And yeah, you could come up with scenarios to do it, but there's no really good evidence. And then we've, of course, got all sorts of things on habitability, and we have things on things that people thought were life, and now most people disagree, like the Viking, like Mars meteorite ALH 84001, which was announced in 96 to have evidence of life within it, or past life, dead life.
Is that Allen Hills, that one?
Yes, it is named Allen Hills, which is the ALH, and then 84 is the year it was found, and it was the first meteorite found in the Antarctic expedition that year. So there you go. Now I don't need a random space fact.
So what do you got for me this week, Bruce? What's our random space fact?
Have you ever wondered, actually you probably know, ways that if you can't have good resolution on a planetary body like Uranus or Neptune, and you want to figure out what the wind is doing, how would you do that? Or what do you do if you want to study the somewhat deeper atmosphere of, say, Jupiter with a spacecraft that's, say, named Juno? Well, you use microwave. You basically use radio waves, microwaves. You cook your hot dogs and simultaneously study it's passive microwave studies. And the other key thing is always Doppler shift. So you look for particular bands in the microwave and look at the Doppler shift of whether they're moving towards you or away from you and how fast, and you can start to build pictures of wind patterns. You can do a lot of other things with the microwave, and it is a terrifyingly complicated thing to do, but it produces results that no one else can.
One of my favorite things from the NOAA website is looking at the actual wind patterns on Earth and seeing those big simulations. I would love to see something on the scale of Jupiter like that, with all the little lines drawn out so you could see where all the wind patterns are. I mean, why would it be useful? Who knows? But I'd love to see it.
Oh, you should check the literature. I think there are people who've tried such things. Certainly, and Mars has a very elaborate global climate model simulation. And of course, it's at least as complicated as nailing the weather here, which is a challenge because it's such a complicated system. And there we don't have all sorts of monitoring stations. So it's a lot more fanciful, but people think about such things. Not I, but people think about them.
That's cool. One of these days, I'm just going to envision a world where we have weather reports from all of the different planets on the news someday.
All right, everybody, go out there, look up the night sky, and think about something totally different, like a chimney. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio. But before we go, a reminder that our Day of Action to Save NASA Science is coming up on Monday, October 6th in Washington, D.C. Seriously, thank you to everyone who's joining us in person on Capitol Hill, and to all of those who've taken part in our Save NASA Science campaign. Also, a huge shout out to the many organizations that are partnering with us to bring the message of space science to Congress next week. To my knowledge, this is the first time in U.S. history that this many organizations and this many people are going to DC all at once to speak with our representatives about why NASA science matters. If you can't be there in person, you can still make a difference from home. We'll have easy actions for you at planetary.org/action. Or you can learn more on our Save NASA Science Action Hub at planetary.org/Save NASA Science. If you love this show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry to planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members. Tens of thousands of explorers on Earth who share a passion for unlocking the secrets of Mars and the rest of the cosmos. Their support fuels missions like Perseverance and the search for life on Mars. You can join us and be part of that adventure at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Casey Dreyer is the host of our monthly Space Policy Edition, the next episode of which is coming out on Friday. And Matt Kaplan hosts our monthly Book Club Edition. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. I'm Sarah Al-Ahmed, the host and producer of Planetary Radio. And until next week, save NASA science and add Astra.